now. All right. Does it say it's recording for you guys? It's all good?
Yep.
All right, cool. All right. And then let me share my screen as well. Yeah. Okay. So you guys can see my presentation over here?
Yeah.
All right, cool. All right. So basically, what I had intended was just going through this presentation and then going into the CAD a little bit, and just getting guys a little bit more familiarized with the powertrain stuff, like the components in there, and then also just getting to meet you guys as well. So this is the first time meeting. What's up? But yeah, so I guess with introductions out the way, let's get into it. I'm gonna try to keep this like kind of light. I don't want to be droning on you guys. You know what I mean? There's a lot of text in my slides just because I spam when I make stuff like this. But I'd say definitely listen more than read. The text is just there in case you guys ever go back to it, whatever like that. But yeah, that's the gist of my my layout. So I'll go over the basic stuff, and then I'll go more into the CAD of the car to show you guys what we're dealing with, basically. All right, so about me. So this is what I look like, my beautiful face. Oh wait, hold on, let me just get how do I see the chat? Can I see the chat? Oh, doesn't even show it to me. All right. Hiram, just let me know if they say something.
Yeah, sure.
All right, cool. All right, so yeah, this is me. I'm a senior mechanical engineering. I've been a member since like the first day I came on campus. I was I was really, really excited to join this club, to be honest. And yeah, I like knew about the club, and it was one of the reasons I went to Stony Brook, because of the club. But yeah, I've always been excited for the club. I really like it. I think it's probably one of the best things anyone could do in like their professional career. Seriously, like this club, it really makes you stand out. You know what I mean? That's like the one piece of advice I give to everybody. Like, this club really genuinely makes you stand out, because at the end of the day, everyone's going to have a degree, but like at the same time, you're going to have this thing to set you apart. You know what I mean? You're going to have some like professional development, learn some real skills, whatever, learn to work with a team, everything like that. It's, and also competition is the funnest thing I do all year. And I genuinely mean that. I seriously do. And, but yeah, so I became gearbox lead sophomore year. I was working with the president a lot at the time, and I got really close with him. And he was like, "Hey, we have this guy who's leaving, and you want to become the gearbox lead?" And I was like, "Oh yeah, sure." And back then we had a lot less positions. We really only had we didn't really even have systems. We just had subsystems. So we expanded our crew, basically, like our structure of the club, so that way we can have more people in more positions and less load on people. And it really did help. It's pretty good. So I became gearbox lead, and then in my junior year we decided to restructure the hierarchy, if you will, and then I became powertrain lead. So yeah, that's the development of things. I worked at Challenge Electronics 2 years ago. They made they basically do like audio equipment for stuff like that. And then now I work for Northrop Grumman, which is pretty cool, in my opinion. I like the company. It's pretty cool. And then yeah, basically my last bullet point, I make car go. Yeah. And so here's a couple pictures of me on the right, and there's just one of me in the driver gear. One day we were doing testing. I was the driver. There I am. On the right, the top right, that's a picture of me at competition. We have this thing called the design event. I don't know if you guys how familiar you guys are with it, but the design event is basically just going up to actual engineers, and then they're like, "Hey, show us your car. Show us how you designed it. What conclusions you made, what you changed, why you changed them, how you validated them, whatever like that." So, being lead, I led the presentation over there. So that's me in the middle of trying to explain something. I don't know what. It was probably mumbo jumbo. But below that is me at competition, my first competition. I was in this thing that they used to call Carnage Crew, where it's literally all the cars that get stuck. You got to help them get out, and it's like an unbiased thing. Like you're there to help out everybody, not just your team, obviously. So any car gets stuck, you help them out. So that was me. That was my job. And then there's this team to our left. It was a Chinese team, and their stuff like got stuck in customs. It really sucked. They weren't able to compete for the first 2 days, but the last day they finally got their car out of customs and they were able to compete. So we were just helping them unload, and yeah, that's the whole team, like with the photo with them after we finished unloading the car. But yeah. All right, next slide now. So now getting into the actual stuff for Powertrain. So the stuff that I'm going to cover in this set of slides, some basic stuff that it's pretty general for anyone in Powertrain to know, right? So we have power in general, gearing, power transmission, materials, casings and housings, shaft/axles, and then testing. Then I also listed out here the subsystems that we have. We have gearbox. We have 2 subsystem leads, one for the front and one for the rear. Stuff's still being organized as we're kind of just like doing work as it needs to be done. So some of these positions aren't really exactly filled right now. And also, like I said, we just recently made the restructure change. So yeah, we have gearbox, driveshaft axles, and CVT. The subsystem stuff will be hashed out more next week. This meeting is going to be more for just like general knowledge about like components and stuff like that, right? So all right, so getting into it, right? So the first thing that we have is power in general, right? So like, what is power? You know, you guys get like cars, you get like horsepower ratings on them, and like, you know, obviously the bigger the better, right? But like, what is power? So power is composed of 2 primary things: the speed that you're well, in our case, when we talk about engines, right, we primarily focus on the rotation speed of the shafts or whatever you're talking about, and the torque of that shaft. So torque is just basically the twisting force. So like how much force the shaft has as it rotates. So you can imagine something with the small torque. If you were to put your hand out and grab it, like a rod that was spinning with very low torque, you'd be very easily able to stop that shaft from spinning, and you barely feel anything. But if a shaft had high torque, you were put your hand out in there, you turn into a frisbee. So it's not very you know, yeah, it's a very big component of power. The other thing is revolutions per minute, the rotational speed of whatever shaft you're talking about. So you can have really high torque but spin it at like 0.1 RPMs. That's not going to get you that much horsepower. But if you have a lot of torque and you're spinning that thing fast, yeah, you have a lot of power to deal with, right? So our engines have 10 horsepower as a standard thing. Everyone gets the same exact engine. Everyone gets the same exact power. Everyone gets the same exact governor. Governor is just basically something that limits the speed of the engine, the rotational speed. So yeah, everyone has basically the same setup, and do with it what you will, basically, and that's how you get different performing cars. And then a large goal of a powertrain is to manipulate speed and torque without breaking something, right? So the 10 horsepower compared to like cars, like regular road cars, it's not a lot, right? But 10 horsepower with the amount of torque that we had, like I said, it's a twisting force, right? So stuff can very easily break, and stuff does, in fact, very easily break. So what we basically have to do is manipulate rotational speed and torque to get what we want out of each, while at the same time making sure that nothing fails, you know? So we have a whole bunch of different ways to do that. Testing, FEA analysis, and you know, the fan favorite, if something breaks, you got to go back to the drawing board. So yeah, there's there's that. So that's the
Chief Fun has a question.
I still don't know how to open up the chat.
That's kind of weird.
Yeah, hold on, let me see. Oh wait, oh crap, how do I? Okay, can you just read it to me for now?
Oh yeah, sure. Would an example of high torque, low speed be going uphill or no?
High torque, low speed, yeah. You would definitely want high torque going up a hill. And that is actually one of the events at competition. So they have two different types of events. They have they have two different types of events where you actually drive the car. They have these smaller ones that test certain aspects of your car. For example, they have a suspension one, they have an acceleration one, and they have a hill climb one, right? So for hill climb, what you really want is high torque, because you have to be able to get up that hill with this like 400-pound car, right? So it's not very easy with the amount of power that we have, but with the torque that we have, we are able to do it, right? So if we were spinning the wheel super, super fast with super little torque, yeah, with this car, it's not going to have enough force to carry the sheer weight of the thing, right? But if you have very high RPMs, obviously you go faster, right? But without that torque, you're not getting up the hill. So yes, uphill climbs is an example of high torque, low RPM. So yeah, that's a good question. Yeah, that's a good analysis too. All right, so the next slide. Power. Oh, this is just okay. So this is more of what I was talking about. So you can see over here, this torque power curve, right? So this is very typical for looking at engines. We usually deal with in Baja is what you see on the left over here. So now these are the exact power torque curves for our engine. This is exactly what we look at. This is what Briggs & Stratton, the manufacturer of our engine, gives us. So you can see here that on the first one, at lower RPMs, the engine just produces less power, right? So when there's like no throttle, we're only about making 5 horsepower, right? But once you floor it, you go all the way up to 36. That's when you get up to the peak of power. The things like spinning at full revs and everything like that. It has max amount of gas going into the cylinders, and it's making the most amount of power, right? Below that, you can see the torque curve, right? So as I said, from like the previous equation over here, right? If RPM increases, and then torque has to go down in order to keep the same amount of horsepower, right? So that's basically what happens typically. So as RPMs increase, torque goes down, right? And then you can see that over here. So we start to hit a maximum, and then torque goes down. So yeah, from these graphs, we can see that our 10 horsepower engine actually only makes 9, woohoo, and our engine also caps out at about 14 foot-pounds of torque, which is a considerable amount. So what we do is these wheels, like at the floor, they spin at like probably maybe somewhere in like the 300 RPMs, something like that. I don't have the number off the top of my head, but it's definitely not past 500. So our engine spins at 3,600 RPM. So you can see how that kind of has a pretty big delta, right? So that's what Powertrain is there for. That's what we have to do. We have to get 3,600 RPM down to whatever the wheel needs, and doing so will increase torque, right? Because like I said, with this equation, you decrease power, then you have to increase torque, right? So our car actually has at the wheels around 400 foot-pounds of torque, which even by like the metric of road cars today is an insane amount. It really, really is. So yeah, so there's a lot of validation that has to go through this, and that's where the testing lies. All right, so moving on, the next thing we have is gearing. So oh boy, are there a whole bunch of different types of gears. All right, so from this picture, right, I'll focus on these black and white ones. There's a large variety of different gears for basically a lot of different things that you want to do. What we primarily use are what you see like over here, down here. These are called spur gears. Oh, also right here. These are called spur gears because they look like spurs, basically, right? And so that is like our bread and butter, I would say, spur gears, because spur gears are pretty simple. Like we actually make them ourselves. We take a big plate of steel, really a half-inch thick steel, and we use our EDM machine, which basically has a really thin wire that has a really high current, and it goes into the metal, and with the current, it basically just melts it, and it's super, super accurate, down to a 1/10 of a 1,000th of an inch. So with this accuracy and this manufacturing capability, we're able to make these gears on our own, and we can make whatever gear we want. You know, we don't really have to go to a manufacturer and say, hey, can you make this gear, because we'll make it ourselves. It's pretty interesting. It's pretty cool. I like doing it. I primarily do that. Like look over all the manufacturing. I used to do all the manufacturing myself. But now, like I said, with more people, we've really expanded, and it's a lot less workload now. So more manageable, I'd say. But yeah, so that's our bread and butter, spur gears. Another type of gear that we use on this car is this one right here. This is called a bevel gear. And so the one thing that you can notice is that these gears aren't in the same plane. And what I mean by that is, like, you see how these two are basically, you can just like lay them flat next to each other and they'll spin fine. These don't. Their axes are 90 degrees set apart. So pretty similar to these over here. This is called a bevel gear. This is called a screw gear. Yeah, they might also call something like this miter gears. But it depends with like the configuration, because these the axis over here coincide. They intersect at some point. Meanwhile, the axis over here don't. Yeah, these are called screw gears. This is called a rack and pinion. So the pinion is the gear, and the rack is this part down here. And this is what they use in the steering rack, right? So that's why they call it a steering rack. It's because that's what this is. It's just this part's the rack. So when you turn the steering wheel of the car, you're turning this, right? But then the wheels move left to right. So how do you get that motion? It's through this system. You turn the steering wheel, that turns the gears. This gear then turns this rack left or right. So it's pretty interesting. The next one over here is a planetary system. So stuff like this has typically like super high gear ratios. Stuff like this, you can get like 1 to 1,000 gear ratios. And I'll go into what that is a little bit later. This is, again, like a planetary gear, but just without some of the other gears. You can have a different configuration. So you can either like spin this gear or just one of these, and you'll get like a pretty similar motion. These over here are helical gears and double helical gears. So you can see over here that these teeth are flat and they're straight. Meanwhile, over here, these are slanted a little bit. So stuff like this will actually get you some different type of properties. So typically, these can handle more torque, because with a slanted face, you actually increase the surface area of contact. And because of that increase in surface area, you can then carry more force. So they are kind of preferable sometimes. They also are quieter, but they are a lot more complicated to produce. We actually can't make these. The reason we can make these is because these teeth are straight, and if you can imagine a wire trying to cut this, it would be pretty simple. It just does the profile. But the wire in our machine can't do slants like this, so it's just not feasible with our manufacturing capabilities. They're nicer, but not required. So we can't make them, so we don't make them. Same thing over here, just unmanufacturable for us, but again, has a lot of advantages if you can manufacture it. So these are typically used in like industry. Like your cars will always have these, because if you had straight cut teeth like these, your gearbox would be louder than your engine. So yeah. Oh, oops. And then, here's some more examples of bevel gears. Yeah, this one is a straight toothed bevel gear. This one's actually a miter because it's a 1-to-1. There's the same amount of teeth on both sides. And then this is a spiral, just like this one. It's a spiraled version of the original. This one over here is called a worm gear. So it has a pretty interesting type of gear. I guess it's kind of shaped like a worm. I don't know, but yeah. Then you have some other things than gears. You can also use belts, right? So this is called a timing belt. And the reason it's called a timing belt is because it has these teeth in there. And so that way you will never have slip in the belt. If there was no teeth, you could potentially slip. And then let's say if the torque's too high and this one's trying to spin this one through the belt, but the belt can't spin it because you have way too much force, then you're going to slip. But with these teeth, there's no slipping. You know what I mean? those teeth make sure that if one spins, the other definitely does as well. Pretty similar to a chain, all right? You can imagine like these teeth and these sprockets going into these little cavities on the chain, right? And so if one of them moves, if one of those sprockets move, the other one has to move. So it's a pretty similar concept. This is what a straight belt would look like. This is what our CVT looks like. So the CVT does all the gearing for us, right? It's a pretty complicated like setup, but we don't manufacture it. We just adjust it to whatever needs we have. So basically what happens is this thing will move in and out, and so will this, in order to change the diameter of where these pulleys make contact, right? So over here you can see that this pulley goes in. Sorry, hold on one second. I'm trying to see if I found the chat. Wow. Okay. Nice. SMH. Oh, Zoni's here. I didn't even see. Okay. So yeah, you can see these. Where was I up to? Oh yeah, the CVT, right? So you can see that this over here has a pretty small diameter compared to over here. The belt makes a lot larger loop over here compared to over here. And then so what this CVT does is this will move inwards, which means that the belt will actually increase in like a radius. And over here, this will move outwards, which means this belt will move in and the radius here will decrease, which means if you have two different changing radiuses, you're going to have different gearing, right? So that's basically like a gear ratio. It's like how many teeth on one gear compared to the other one. And the gear ratio is important because it'll tell you how the RPM and torque are going to be affected, right? So for example, if we're looking at this one, right? And this has, let's say, 20 teeth. And this one over here has only 10. So there's a 2-to-1 ratio, right? And so what that's saying is that the speed is going to be, depending on which one's your input. Let's say that this one is the input, right? So you spin this one, right? This one has 40 teeth, 20 teeth, and this one has 10. So since this one has 10 teeth, there's a lot smaller distance to cover in one rotation. And since it does the same, it does a rotation in the same amount of time, but over a smaller distance, it actually will increase in RPM. So the smaller teeth, the smaller gears, increase RPM, but they have a decrease in torque, right? It always has to follow that same rule. If you increase RPM, if you increase one, you have to decrease the other, right? So the small gear here, because it has a smaller distance to travel, increases in RPM, but it decreases in torque. And vice versa happens for this big gear. If this one was spinning, this gear would only spin half as fast, but would have twice the twisting force, twice the torque. So yeah, so that is like the bread and butter with gears. The gear ratio determines how the power is going to be manipulated, with respect to the RPM and the torque. So the key thing to remember is bigger gears will have lower RPMs but higher torque. Smaller gears will have higher RPM, lower torque. All right. Let me see if there's anything that I missed in the chat. Why
from Abhishek?
Why don't bikes use that? Why don't bikes use what? I'm sorry.
CVT.
Why don't bikes use CVTs? Okay, so bikes don't use CVTs because of the issue that I stated before, where you can have slip, right? So CVTs are really great until you get into high torque territory, right? So if like I said, they don't have teeth. So if you can imagine, this side is the wheels, right? So let's say that your wheel is stuck and does not want to move, right? And you're trying to get out of there or whatever like that. So you tell the engine, hey, make a lot of power. I need to get out of here, right? And so this is the engine side. This is the wheel side. Wheel side says, no, I don't want to spin. And the engine's like, yeah, I'm really spinning. So what you're going to have is this belt's not going to be able to pull this. It's just stuck in place, right? So this belt is just going to slip against this side of the CVT. And so you're not going to have any rotation, and it's just not going to work. So bikes don't use that because you can have slippage. Also, this is kind of hard to get in a really small form factor. This thing relies on like the moment of inertia of masses and stuff like that. So there's literally weights in there, and you just need the actual space for those weights to move. So adding something like this would be really bulky for a bike, and it's also just not really simple. Fixing something like this, like on the go, on the fly, it's just a little bit more complicated compared to just a chain, where it's literally just a chain and two sprockets, and that's it. But if you use a timing belt where there is a high reduction in slip, you actually get a lot better performance. And motorcycles do use belts. So if you want to apply this stuff to a belt, you wouldn't really put a CVT on a bicycle, but you can put a belt on there, and specifically one with teeth, so that way you don't get that slip. But yeah, that's basically belts. Okay,
Yeah.
I gotta keep it moving. All right, powertrain. Oh no, wow, power transmission. Okay, so power transmission. So typically we have two goals over here. So we can either move power from one location to another, and when I wrote that, I meant more like the axis. So what I'm saying is something like this miter gearbox. So this is one of the designs of our miter gearbox. So these are the gears that change the direction of rotation 90 degrees, right? So you can see this is our input and this is our output, right? So typically what you have is something where the axes are parallel to each other, right? So on the CVT, this is the input and this is the output. You can imagine the axis of rotation for both of these, and they're parallel, right? But over here, they're perpendicular. And so the reason we need this is because we need to get the power from the rear to the front. So our engine is spinning. I don't know how to. I can annotate. That's cool. Okay, so our engine is spinning in this direction. We need to get it going forward. So we need this miter gearbox here, and then that way we can get a shaft going this way, and then we have another gearbox in the front that brings power to each wheel. All right. So, yeah. So yeah, that's niter gearboxes. That's one reason you need a gearbox. Another reason is for the manipulation of these gear ratios, right? So that's what this rear gearbox does. So you can see that there is actually 4 gears in here. One of them is just hidden behind the bearing over here. It's pretty small, but yes, trust me, there's a gear back there. It's very small. And then you have 2, 3. If you can see these teeth, that's a third one, and then this is a fourth one. And so the reason why we have so many gears is, like I said, we have a very high RPM, but we need a very low RPM. So this gearbox reduces the speed by 7.365, right? So for every 1 rotation of the output, you get 7.365 rotations of the input. So yeah, this is a reduction box since you reduce the speed. And so yeah, that's one reason. That's one giant reason why we have gearboxes in the first place. So you can see this also, the actual thing down here, right? So you can see the gear I was talking about is right there, and then you have 2, 3, and 4. This is an older version, so this actually has a differential in there. What we use now is a spool. Differential. I didn't cover it actually. Wow, I completely forgot about differentials. But that's a little bit more in depth and a little bit more specific because differentials are a little bit complicated to explain. But basically, when you're going around a turn, the 2 wheels on the left and the right need different speeds. The one on the inside turns slower because the one on the outside has a larger distance to travel. So they have different speeds, and differential basically delivers power to both wheels while allowing them to spin at different speeds. You can have it and you cannot have it. It obviously sucks for handling if you don't have it, but it's a lot lighter and a lot cheaper. Some fixie bikes aren't that bad for New York. You can use belts, but then they're set to 1 ratio. Yeah. If you just use a belt, that's why the bikes usually have like nine different sprockets on them. You can see you ever see the back end of a bicycle? There's a whole bunch of those sprockets just so you can get that gearing. You know, these have an infinite amount of gears, but bikes like that, you know, they only have like the 6 or however many sprockets there are on that thing. So you're comparing 6 to infinity, you know, but at the same time, this thing is a lot more complicated, and it can be pretty expensive. Okay, so this is typically done with the gearbox of some variety. Yeah, so you can either, like I said, you can either do a gear reduction, you can do a beveling, or you can do both. You can honestly throw this in there. It's a little bit complicated, but you can. We don't do it because, like I said, it's complicated for manufacturing. With our limited capabilities, we really have to make sure that what we design, we can make. So that's why these two things are separate. But if we had some really, really Tony Stark type of stuff, you know, it would probably be a lot more doable. Gearboxes, I can't read that. Gearbox can also change the direction of rotation. Oh, yeah, that's what I was talking about with this thing over here. How these axes are perpendicular to each other. All right, next, materials. All right, so material selection is very important, obviously. So when you're selecting materials, you typically have to think of what are my physical requirements. So like, how much force does this material need to be able to withstand, right? So and the capabilities of each, but yeah, so the requirements and the capabilities, right? So you need to know how much force the material is going to see, and you need to know if that material can take it. The next thing is some materials have desirable properties sometimes. Okay, so for example, there is a very large amount of steels, right? So if you see on the top right, there's this chart. That is all the different types of steels by class, just class. There is a lot more in depth than this list. So you can see they say like 30XX, 40XX, 51XX, right? So each one of these classes then has like a subclass. So for example, there's 8620 and 1144. Two very, very different types of steels. One of them has chromoly in them, and the other one doesn't. Chromoly makes oh wait, no, that's 6130. I'm sorry, I'm thinking of the wrong steel. Okay, so for example, 6130 has chromoly in it, and so that makes it just very, very how do I explain it? It's very good for absorbing energy, I guess. So that's what they make the frame out of, actually, right? The frame is made out of this 6130 type of material. And then we have different type of steel, 1144. 1144 is very desirable because there is this one operation that we have to do on some of these metals called heat treatment, which is basically where you make the steel harder. But if your steel is harder, it's also more brittle, so it's more prone to cracking. So you're exchanging the ductility of the material for strength. And if you basically bend it too much, it's going to break a lot earlier. So 1144 is great because it already is a very hard material. So where we would normally have to harden some materials, we don't have to harden 1144. And hardening is the downside of the hardening is that you tend to warp your thing. Not a crazy amount, but it has affected us before. So it is a pretty big consideration. So, for example, some of the shafts that we use in the rear gearboxes are made out of this 1144 material because we don't have to harden it. If we used 8620, we would have to harden it. And then in the surfaces where the shafts mate with the gears, it might actually be deformed. And they might not just fit with each other. And you can have something break like that. So we choose 1144 because of this one desirable property. We don't have to heat treat it. It's a little bit more expensive, but it's worth it. All right, so the next thing, two primarily used materials are steel and aluminum. Steel and aluminum are bread and butter. Steel is really good because it is very strong. They make buildings out of this thing. It's crazy. So yeah, steel is very, very strong. And it's relatively cheap. So shafts are typically made out of steel because shafts have to see the forces that and transmit them Gears as well. Gears are definitely made out of steel. I've never seen an aluminum gear. And aluminum is great for weight savings because aluminum is like half the weight of steel. It's awesome. So typically when you have really big components, you make them out of aluminum. So housings are made out of aluminum, and some materials that are just big that we want to keep the weight down on. For example, our hubs, that's a component in suspension. That's also made in aluminum just to save weight. It's not as strong, and it's broken on us before because of that, but it's a lot lighter. So we accept it. We accept the trade-off. The next thing is an example over here on our lower and upper lateral links. So if you guys can see well enough, there's a bar that goes right here to the wheel and a bar that goes right here. This one's in black and this one's in red, right? And so this is a perfect example of where we decide to make trade-offs, right? So the lower one is made out of steel, and the top one is made out of aluminum. I'm gonna ask, do you guys take any guess as to why the bottom one is steel and the top one's aluminum? More stress on the bottom. That's a decent guess. That's not a bad idea. All right. Well, I'll go ahead. So the bottom one actually is it's steel because it's closer to the ground. So let's say a rock comes up and gets kicked into one of these tubes and a rock hits it. A steel one would take that pretty well. It would really take it pretty well. We can have a decent amount of confidence that it won't dent our tubes significantly or anything like that. These things definitely do get dent up and banged up. But with steel on the bottom, because it's a lot closer to the floor, we need that strength. Meanwhile, on top, it's a lot farther from the ground, and we have a lot less concern about something hitting it and then denting it. So for weight saving reasons, we make the upper one out of aluminum and the lower one out of steel. And yeah, that's a perfect example of the two trade-offs between the two. The top one, if it gets hit, it is a lot less likely chance of it getting hit. And so, but we can save weight by just making it aluminum. So yeah, that's a pretty decent trade-off. All right, cases. So cases serve to house and support the gears and other components. So the gears need some way to be held up and everything like that, and just somewhere to live, basically. That's what casings are. I don't think the definition of casings is anything too beyond anyone here. But yeah, typically basically these cases, what we try to do is we try to conform it to what we want, what we have inside there. I mean, so you can see on this top example, those gears are in the positions where they just need to be. They can be somewhere else, like they can move a little bit, but this position allows us to make sure that it connects to the engine properly, because there's a center to center distance between the engine and the gearbox. It has to be 8.5 inches apart exactly. And then also the output of the rear gearbox has to be wherever the wheels are going to be, right? That has to perfectly line up with those wheels. So we know where these gears should be because we know the distance between the center to center and the wheel. And so we put in the gears and then we say, okay, we need to make a housing for these gears. So you have to go in and basically design a profile around it. My rule of thumb is keeping the case 80 thou away from the gear. So if you can see, there's slight clearance over here. There's slight clearance over there. There's slight clearance over here and slight clearance over there, right? So that's all just like the form factor of these casings. So we have to make sure, obviously, that these gears don't hit into the casing. And typically, we keep it 80 thou, which is 80 thousandths of an inch away from the cases. So, yeah, that's that. Oh yeah. Also, these cases, these are very, very extensive in production. Like this the picture on the top. Unless you can find the casing over here, you can see like these lines, and that's where the end mill on our CNC just went around and cleared this entire area out. And so this started as one giant block of aluminum. Took us about a month or so to make. It's very, very long. It's very, very intensive, just because you literally have to take this giant block and remove all of this material at a very slow rate, and then you have to go in and make sure that these bearing pockets are the correct size and all that. And if they're not, you have to go back in, machine it again, make it like just this little area, do it again, do it again. You can't make it too big, or else these bearings won't fit in there. So it's very it's very time consuming. So we have to make sure that these cases are take manufacturability into account. We can't make something that's overly complicated to make, or else we're just going to end up like spending a year making a case. So it's going to be, yeah. So that's why we're trying to reduce the number of cases in our design for REVB, because we have 3 gearboxes right now that we don't think we need to make. And if we don't need to make them, we will definitely not make them, because that will take so much time. It would really, really save it would really, really save on time if we can get these things to be made without these 3 gearboxes. All right, the next thing is drive shafts and axles. Okay, so drive shafts and axles just carry the power over a distance, right? So if you have you can see over here, this one really long drive shaft that goes from this box all the way up to the front of the car, right? And then you can also see these small, a little bit smaller ones. These take power from the gearboxes to the wheels. So the wheels go on this right there. That's where the wheels go. So there are 2 primary types of I'm just gonna call them shafts. There's a CV joint and a U joint, right? And they each have their trade-off. So over here on top, this is a CV joint, and down here, this is a U joint. So you can see one very clear, distinct difference is how they are rotating. So over here, there is not a lot of variation in like the rotation. Like this just seems to be spinning fine. You might not even think that there would be an issue with something like this, but what you actually get on a simpler system is this. So if you were just to connect 2 things together pretty simply, here's okay. If you were just connect 2 shafts simply like this, then you get this motion where with the increase in angle, it like kind of jerks. It really, really jerks, and that's not desirable at all when you're making something in for like powertrain. So yeah, in some cases it is okay. Like for example, some teams they run these U joints in the rear, because like I said, it depends on the angle, right? So if the input and the output are parallel, you don't actually really see any difference. It does act normally, completely normally, but with this angle like this, you get this severe jerking motion that we can't deal with. So in the front, right, where you have the wheels that turn left and right, the turning of the wheels do create this unalignment, right? So if you're turning the wheel left, but these inputs stay the same axis, meanwhile the wheels change, you're gonna have this jerking motion happening to the front wheels in a front wheel drive system or all wheel drive system, right? So like for us, we're very concerned about that. So we cannot use U joints in the front, because once those wheels turn, you'll get an action like this and something will explode. And I very much mean explode. And yeah, that's pretty much shafts. The last thing, I think this is the last thing that we have. Oh, there's a couple more. Oh, okay. Last thing I have right now is testing. So testing, we do a couple different forms of testing. So CVT definitely takes the lion's share in testing in our subsystem. So over here, you can see, we just took a nice little photo, but this was basically in the middle of a CVT test. I don't know if you can see it, but the case is actually not on the CVT because they were just hot swapping some setups. So yeah, there's a lot of testing that goes on CVT wise. That's like basically all they do. It's pretty interesting because they're definitely the most that go out and see the car drive. And they also work in another thing called the dyno, and the dyno stands for dynamometer. And basically, instead of putting the CVT on the car, they put it on like an engine with a test setup already. so they can actually get these acceleration curves on a computer and all that. So it's pretty interesting. I think it's being worked on right now because I think there's been some issues with the dyno, like just working in general. So there is that. We also do FEA testing. FEA testing is awesome. FEA testing is just going on a computer and you type in like the physical properties of something, and you type in your loads and you say, based on this load, will this part fail if it can withstand certain amount of force, right? And the computer, based on your geometry, will tell you yes or no. So you can see over here, there's red spots and blue spots. Blue spots basically say there's no force here, there's no stress here, this part is totally fine right here. Red parts say, wow, there's a lot of force here, but doesn't necessarily mean it's going to fail. And this part passed, even though it's red, it just shows like where the concentration is. It never was really close to failing. But yeah, this is actually what replaced the differential. This part over here, what I was talking about before in like this picture. So this was a differential. Right here is where the spool would go. But yeah. And then sometimes we also use these things called strain gauges, which is basically these little like stickers that you can put onto a part, and then you can kind of like twist and pull the part however you want to, and the stickers will read the amount of deformation it sees, and it would output that out to a computer, and you can test how much strain your material is seeing. So it's pretty interesting. But yeah, that's testing. And that's basically a lot of what I was going to go over for basic knowledge of powertrain. But yeah, okay. So overview of REVB. So this is what we're going to do for this year, right? There's only 2 more slides, so the overview for REVB. So here we have a very simple layout of our car. We have the engine, and the CVT goes right over here. So the engine connects. The CVT connects the engine to the rear gearbox, and right aside it, we're going to have our miter gearbox. And this miter gearbox is actually going to route the drive shaft under the engine all the way up to the differential, which then brings power to each wheel, like I said before. So the way this varies in our old design was we used to have this gearbox go to the side of the engine, and then there would be another gearbox right about here. So basically another gearbox would have been here, and then we also had 2 more over here that basically extended out like this, and then the axles went out this way. So we are trying to cut down on 1, 2, 3 gearboxes, and that would, like I said, the manufacturing time is ridiculous. So saving this amount of space and these amount of manufactured components really, really does save us so much time. And we really want to try to figure a solution out like this for REVB of the car. So stuff to do. So like I said, remove those portal boxes. That's the ones that were at the front. Remove those 2. Raise the engine. We want to put that shaft under the engine instead of alongside it, like how we had it before. Optimized rear gearbox goes on diet. Yeah, basically this rear gearbox, we could make it skinnier, because when we removed the differential from there, that was the only thing making it as wide as it was. So removing the differential basically lets us make it as skinny as we want. So yeah, the rear gearbox may go on a diet. We also have CVT cooling. So the CVT, this is a giant enclosed box, and CVT produces a lot of heat because of the belt. So we really need to find a way to get that heat out of there. And we have my friend Sarah Worsham was working on that. She's designing fins, so it's some thermal work. It's pretty interesting. Yeah, it's a little bit more. I wouldn't say higher level. I mean, yeah, it's very interesting. It's she does more thermal stuff while we do more hardware stuff. So, yeah, that's pretty cool. Axle optimization manufacturing. So currently, as is, our axles are very wonky, to say the least. It's basically we need to buy 2 axles in order to manufacture one of our axles. the reason we can't just buy an axle from like another ATV or something like that is because those axles are too short. They're like 99.9% of the time too short for us. So we have to actually manufacture our own. And because of a lot of reasons, it's just kind of difficult to do so. Oh yeah. Like we have to buy 2 different types of axles as is right now. We don't want to be buying 2 axles to make one. So we would have to buy 8 in order to make 4, which would run us, maybe like 5. No, maybe way more than that. Yeah, a lot of money, a lot of money, yeah, and a lot of manufacturing waste that we don't want. So these axles actually have to be optimized. Try to get them to be made in only one part if they can. That would be awesome. And adjusting the miter gearbox location, right? So as is, we have a solution to mount this thing. But we want to find a little bit more of a robust system. So this, the mounting here will have to change. It's gonna need some brainstorming. But also we want to move the location because, like I said, this used to go around the engine, but now we need to go under. So the location is just gonna change because of that. And that's pretty much all I really had for the slides. Let me stop sharing screen. All right. Yeah, that's my big spiel. Yeah. So, is there any questions so far? Anything Powertrain? I'm sorry that if it was really droning, but I hope you guys were able to get something out of this. Just it's just some basic background knowledge about the car in general and all of that stuff. Just basic stuffs that you could know. You don't really need to go in depth on every single one of these. A lot of this stuff don't really use every day. Like, for example, that gearing slide, we don't use most of those gears. We really keep it down to like 2 or 3 of those things. Materials, you pick materials when you're making something. But like I said, you really like learn this stuff as you go. So if we're making something, someone's going to be there to help you out and to teach you, like, this is what you should do. Now you should take into account materials. Now you should take into account testing, FEA. Now you should take into account manufacturability, whatever like that, you know. But yeah, any questions? Anything?
I think Keithan had one.
Uh,
If you feel comfortable, you can unmute. Or you can just type in chat. I can read it for you if you want.
No, I didn't have any questions.
Oh, I think you just did the clapping one, right? Yeah.
Oh, I thought it was the waving. Okay.
No, yeah. All right. Yeah. That's all I got. So, if you guys don't got any questions, that's really all I had. So, I guess I'll see you guys. Yeah, we can call it for now. I'll make another meeting. I do want to ask something though, is because I forgot to make these meetings on the weekends. I don't know if you guys are more available on the weekends. If you guys would prefer the weekends, we could do after the design meeting, like around 11 a.m. or something like that. If you guys prefer that, I don't know if you guys are free or not. I just forgot to bring it up.
Wait, can you repeat that?
When I was making the time for this meeting, I forgot to list the weekends as an option. So I wanted to know if you guys like preferred the weekends or a different time, like anything.
Yeah, I think that would be better.
The weekends, like you think like right after design, or like what are you thinking?
Yeah, like 11 a.m.
Something like that. Yeah.
Mm-hmm.
What about everyone else? What are you guys thinking?
11's good.
Yeah.
11's good.
Okay.
Works.
All right, cool. So I think I would probably make these meetings on Saturday around 11 after our design meeting then, because I think that also works out. We're missing one guy. I think that also works out for him too. So, all right. I'll try to. I think if everyone's cool with that, I'll try to plan the next meeting. And like I said, expect it for next Saturday. And we'll be going over subsystems and stuff like that. And might be giving you some example works to work on, so you guys can get familiar with CAD or whatnot. You know, nothing crazy, just literally getting you guys exposed. You know what I mean? But yeah, I'm gonna stop recording now.